times the derivative of g. So there would be a multiplication of derivatives, and the thing that a lot of students mess up, unfortunately, is that you have to remember to evaluate this derivative not at x, but at g of x. But the point is, there's a multiplication of derivatives taking place. Multivariable case. Suppose we have a function f of x, y, and z, but then we're going to evaluate it on a curve in space where x of t, so x, y, and z all depend on the parameter t. The question is, what is the derivative of f with respect to t? Not x, y, or z. Well, in this case, there's going to be, in a sense, a multiplication of derivatives, if you will, but it's actually going to be a dot product. So it's going to be a dot product of df dx, partial f with respect to y, partial f with respect to z, dot product with derivatives of x, y, and z with respect to t. If you have functions that not only depend on several variables, but return several variables. So a function from x, y, z to u, v, w, for instance. And you're applying a chain rule, if you're changing all three variables into three other variables. You're actually performing a matrix multiplication of Jacobian matrices. So there's still a multiplication going on, but it's a matrix multiplication, not just an ordinary multiplication. Another very important problem that you covered in single variable case, finding a minimum value of a function. You have a function f, you want to know where it has a minimum, take the derivative, and you find where f prime of x is equal to 0, and once you do, then how do you know if it's a minimum? So check if a second derivative. So if it's positive, it's a min, negative, it's a max. If it's equal to 0, it's inconclusive, then you need to do what you were describing, checkpoints on either side. Now, what happens in the multivariable case? We'll just talk about a function of two variables. Now we have finding a minimum value of a function of x and y. So what you do is find a point, call it x naught, y naught, or it could be more than one, but find a point where both partial derivatives are equal to 0 simultaneously. All right, so in other words, the gradient of f must be the 0 vector. So that's a generalization of finding where the derivative is equal to 0. Now what about this second derivative test? All right, instead of the second derivative being positive, you check if this matrix is called the Hessian, which consists of second partial derivative with respect to x and then x again, second partial with respect to y, and then on these spots you have mixed partial derivatives with respect to x and y. I've written them in the opposite order here, but under appropriate, usually satisfied assumptions, these are actually going to be equal. So we check if this matrix is what is called positive definite. It is the generalization of the notion of a positive number to matrices. It is not satisfied simply by all the elements being positive. That is not enough. So the conditions actually get a little more to linear algebra than I want to get right today. If you've seen any of this stuff, it's when the eigenvalues are positive. But anyway, we will come up with some conditions to confirm whether this is positive definite or negative definite to check for a maximum. If it's indefinite, it's similar to the case where f double prime is equal to 0 and we need to try something else. We do much the same with integration. So in the single variable case, you compute the integral of a function f of x to get the area under the curve between x equals a and x equals b. So it's the area of its shaded region that this integral is going to compute. Now multivariable, similar idea, but if you're working with a function of two variables, now you're going to get volume. So for instance, we can compute what's called a double integral. Now, because I've written the dy first, it's the innermost infinitesimal here. We actually have y is ranging between c and d, and x is ranging between a and b. And what is this integral actually giving you? So if you look at free space, then we'll have some rectangle in the xy plane, bounded by the lines x equals a, x equals b, y equals c, and y equals d. And then this surface up here, that is f of xy up here. So what we're computing is a volume of that entire region in three-dimensional space. We could make the region a little more interesting without too much trouble. Suppose we have double integral. The outer integral is with respect to x. We're still integrating from a to b, but now we can make these inner limits depend on x. So I'll call this function c of x and d of x. So then what's happening is, between x equals a and x equals b, we're still looking at a region between these lines, but for each x, we actually have curved boundary on the base of this region we're computing a volume of. So this would be the function c of x, this is a function d of x. So now, we still have some surface up here, but it has at least two curved boundaries at its base. Now we can compute the volume of a region like that. So what's happening is, when you handle the inner integral, you're integrating with respect to y. So that's where you're using all of the integration rules you had before. You think of x as being a constant. Once you finish this part, what's left will be some function of x, and you integrate that with respect to x, same way you did in the one variable case. So in this fashion, all of the techniques you learned from 167 and 168, or especially 168, still apply. But some regions can't really be handled very easily this way. It's sometimes convenient to do a change of variables. Now, polar coordinates, Cartesian coordinates x and y were mapped to polar coordinates r and theta, where x is r cosine theta, y is r sine theta. What we'll cover here is two other coordinate systems. They're cylindrical, so that's where x, y, and z go over to r, theta, and z. X is r cosine theta, again, just like in polar coordinates, and z is, alright, boring. But another we will look at is spherical coordinates. So here we have x, y, and z mapped to r, theta, and then another angle which I'll call phi. So x is going to be r cosine theta. It starts to look like polar. Then we have sine phi. Y is r sine theta, sine phi, and z is r cosine phi. And what this represents is, if you look at a sphere, so r is just the distance from the origin. So it plays a role for radius as usual. And then we have a point somewhere on the sphere, x, y, z. So there's r. Theta is if you drop a perpendicular from a point to the xy plane, then here's your angle theta. So it plays a similar role as in polar coordinates, because this is the xy plane. And then the angle phi is this angle. It's a elevation angle. So theta is between 0 and 2 pi. Phi goes between 0 and pi. So when phi is equal to 0, you're at the north pole. When phi is equal to pi, you're at the south pole, because of the cosine there. Another thing that carries over from single variable calculus with regard to integrals, you recall the u substitution. U du is related is equal to f of g of x, g prime of x dx, where u is equal to g of x. So in other words, du g prime of x dx. So how does this generalize in the multivariable case? If you're changing, let's say, x and y over to u and v, and you have functions that define how the original and new variables relate to one another, then the integral, so double integral of f of x y dx dy is going to be equal to the double integral where x and y now depend on u and v, and then you're going to have the absolute value of a determinant of a Jacobian matrix. And then we have du dv. So to explain what this is, that is equal to dx du dy dv minus dx dv dy du, which is actually equal to the determinant of a matrix that has